So it'll pick all of us up, but on the recording, and I'll post it on YouTube. I mean, you could all watch it, but y'all don't let that deter you from interacting with me, okay? All right, chapter 6 is called Quantum Theory and the Electronic Structure of Atoms. Have y'all ever heard of quantum theory before?
I believe it's relating to quantum mechanics and the movement of electrons.
Yes, it's related to quantum mechanics and the movement of electrons. Have you ever heard about it in pop culture?
I think it's been referenced a lot in science fiction shows.
Yes.
I'm guessing it would likely have been mentioned in the Big Bang Theory, given the fact that a couple of characters are physicists.
Yes, it would have been mentioned in the Big Bang Theory. It would have been in Avengers Endgame in the quantum world, right? And Ant-Man and...
I haven't exactly seen many. I haven't really seen much of the Marvel Cinematic
Really?
Universe movies.
Have y'all seen the Marvel movies? Okay.
The only Marvel movies I actually watch are X-Men.
Okay. I used to skip psychology in college so I could watch the X-Men cartoon. I did. It came on at 1:30 and psychology was at 1, and I'd say, yeah, I want to watch the...
The X-Men movies they're pretty deep. They have a really deep storyline.
Yeah. Anyway, quantum theory, y'all, is trying to explain electrons and how they move around in atoms. And so we know this, right? Hang on. Like this, we've seen this model of the atom, right? Where the dot in the center is the nucleus, and those little ellipses around the nucleus are the electrons orbiting it. And that's not what an atom looks like. That's actually called, do y'all remember it's called the Bohr model of the atom? I mentioned that in chapter 2. That model was established by Niels Bohr.
Not very exciting.
And, okay, there you go with your puns. And probably if y'all took chemistry in high school, y'all drew one of these where you did, right, the ellipses around it and put electrons, yada, yada, etc. on the ellipses, on the levels. Okay. So, I mean, what we're looking at in this chapter is scientists trying to explain that stuff. And so, in a first attempt to explain it, we're going to talk about light. And guys, y'all know light is a wave, right? And waves have different properties. What's a wavelength? It's how long a wave is, right? How would you measure the length of a wave?
The measurement in between the crest.
Okay, the measurement in between, like the crest, right? That's a wavelength. Or between the troughs. Okay, but that would be one wavelength. So,
Is the unit hertz?
not for wavelengths.
Okay.
Wavelengths units are going to be in some sort of length unit. Typically, wavelengths are in nanometers. And if y'all remember, it takes 1 billion nanometers to equal a meter. Nanometers are really small. Then, I'm going to draw another wave. What can you tell me about the wavelength on the one I drew up top versus the one on the bottom?
That's a bigger wavelength.
Okay, the one on the top has a longer wavelength than the one on the bottom. So wavelength is one thing we can measure. Another thing that can be measured about a wavelength is the frequency. And this, William, is the units of hertz. Hertz, y'all, abbreviated HZ, that's the units. That's not a test question, but that's what it is. Hertz is the units for it. If you listen to the radio, and the radio station, y'all, those are frequency stations. What's your favorite radio station? You have one? 92.1? Okay, that's megahertz. That's what it is. It's a frequency unit. So what is frequency? Well, frequency, all waves move through space at the same speed. And you guys have probably heard people say the speed of light. Yeah? Okay, all waves move through a vacuum at the speed of light, which is really fast. Okay? So imagine these two waves are both moving. We'll just have them move in that direction. Okay? So they're constantly moving. Every time a wavelength were to pass this point, you would count it. That's your frequency, okay? So if both of these waves are moving at the same speed, and this is your point for measurement, y'all, if I'm counting this one, I'm gonna give you a count for this one. Say this top wave, I'm counting it like so. What would you guys do to the change in count for the bottom one?
Be rapid.
You'd go faster, right? It'd have a higher frequency because the wavelengths are shorter. And so its frequency would be higher. Now, the energy is associated directly with the frequency. Higher frequency, more energy. Okay? So which one of these waves would have higher energy? The bottom. The bottom one. Wavelengths are shorter, but the frequency is higher. There's also, let's see.
I think it's how radiations are classified in electromagnetic spectrum.
Look at that, William. What did I just pull up?
Electromagnetic spectrum.
Electromagnetic spectrum. Okay, this is just a picture from your book. Y'all see the little rulers at the top? Top ruler, I know you might not can see the numbers. That doesn't matter. You don't have to learn them. It's wavelength. The top ruler is getting bigger as we go that way. The bottom ruler is frequency. Well, it's getting smaller per our discussion we just had. As wavelength gets longer, frequency gets lower. Okay, and then here, in this little big black box, we list different types of radiation. And so because these are higher frequency, y'all, these are more energy. So they're more damaging, like gamma rays. Do you guys remember talking? Gamma rays is a type of radioactive waves, okay? Like uranium, plutonium, those emit gamma rays.
You can also find them in nebula, in some nebulas.
Right in outer space. But gamma rays, because they're such high energy, y'all, they're very damaging. And that makes sense, right? That's what uranium's emitting. And then from gamma rays, we move to X-rays. And everybody in here's had an X-ray at some point. And those can be harmful to you as well, right?
That's why you often have to wear that specialized vest or jacket.
Right, that's why we put the lead on and the person that's taking the X-rays goes behind that wall to take your X-ray, and it's not just a regular wall, right? It's usually lead.
Because lead can't, because X-rays have a hard time driving through lead, which it's also.
Right, lead will slow the X-rays down.
It's
And then
also super
ultraviolet, hang on, let me keep going, William. Ultraviolet waves, those are the ones that are damaging from the sun, UV, right? And then right here we have this visible region. Then we move to infrared, microwaves, radio waves. So the less harmful waves as we move that direction. Now, this is the visible region. And this, y'all can see it down here kind of expanded for you. Have y'all ever heard of Roy G. Biv?
Yeah, it's an acronym.
Okay. What is Roy G. Biv?
All the colors.
The colors. What, like if I start over there, red, just let me put the little R on it. Orange, yellow, Roy. Green, blue, indigo, violet. So Roy G. Biv lists the colors from longest wavelength to shortest wavelength. That's the colors of the rainbow, longest wavelength, shortest wavelength. Or anytime, y'all, if you have something maybe in a window at home that catches the light, you know how we can have, I don't know, it's little glass or crystal things that'll catch the light and break it up.
Prisms.
Have you ever looked at light through a prism? How it'll break the light up, or seen that explained? Okay, and we're gonna look at that in a little bit more today as we try to explain electrons and wavelengths.
Those wavelengths are why it's always in that order.
Yes, the length of the wavelength is why it's always in that order. But y'all, that's the only light. The visible region, that's the part of the electromagnetic spectrum that these human eyes can see. Were y'all aware that there are, I'm not talking about animals that are colorblind, but did you know that there are animals that their eyes detect wavelengths outside of the visible region?
Yes.
Did y'all, and I think that's really cool.
Like mantis shrimp.
That they, I didn't know, I don't know which, okay, but that's really cool that they can see things that we can't see, okay? And again, I'm not talking about colorblind animals. That's different. That has to do with the rods and the cones, doesn't it?
Yeah.
Is that right? Y'all probably learned that in biology. Okay, so scientists are trying to explain electrons, and we're going to look back into some of the experiments that they did. The first experiment that I want to discuss with you is called the double slit experiment. And first, y'all, I'm kind of going to talk about them both at the same time. The double slit experiment was done with light. Now, we discuss light a lot in this chapter because light is a wave. But y'all realize what I want to discuss is electrons, because that's what scientists are trying to explain is how electrons move. And so the double experiment was first done in the 1800s, and here's what was done. Light source, there's my light bulb. Y'all would have known that was a light bulb, right? Sure. Okay, a really intense light is, imagine what I've drawn here are two walls, and y'all, we're looking down at the top of them. What I really didn't honestly, that slit would be more here. Okay, we're looking down at the top of the walls. And so you take a really intense light source, and you can, have y'all ever watched YouTube videos of people doing this kind of stuff, quantum? No, I mean, you could do this if you took, you can't do it with a flashlight because the light is not intense enough. But a laser pointer, you can recreate this experiment with a laser pointer. And what you have to do is you have to cover the end of it, and a good cover would be electrical tape because light can't pass through electrical tape. Okay, and then take a little scalpel and draw you two small slits in the electrical tape and let the light go past it. Okay, and you could recreate this experiment. So, first off, when you shine a light at this single slit, the light goes through. Light's a wave. Okay. As the light passes through these double slits, it creates on the back wall, what the lines I'm drawing here, y'all, that's areas of light exposure, okay? And it creates what is called an interference pattern on the back wall. Now this is a new thing I'm using. I'm going to be toggling between two slides. Let me go. I'll come back to this, but let me go show you. This is what I'm talking about. You see the light goes through this single slit, and then as the light, which is wavelengths, goes through the two slits in the back walls, you have these wavelengths that start to interact with one another, and this is the pattern you see on the back wall. So in other words, y'all, what I'm telling you is light doesn't go through here and here and then just produce two light spots on the back wall. Even though it's only going through two slits, look how many bright spots it produces, okay? And that's easily explained because light is a wave. And so these wavelengths start to interact with each other. Y'all, we see the same kind of phenomenon if we're talking about ocean waves passing through two slits. When they hit the shore, it will do this. It will kind of be an etched pattern of high intensity because it's ocean waves. Even it's still the same pattern. Okay, so again, double slit experiment is explained because it's light. Light is waves. That's nothing new. Well, we're looking at electrons. Y'all, electrons are matter. What is it? In order to be classified as matter, you have to have mass and take up space, right? We're matter. We're just much larger pieces of matter than electrons. And so electrons are matter. And so it was thought that if you replace this light with electrons, if you fire electrons at the single slit, as electrons pass through the double slit, the pattern you should see on the back wall, because electrons are matter, then electrons should just hit the wall here and here because they're matter. Well, when electrons were fired at the double slit, that's not what they saw. They saw this. What did the electrons do?
They seem to behave like a wave as well.
They behaved like a wave. They produced an interference pattern. that was totally unexpected because electrons are matter. So, what scientists did is they introduced right here, y'all know what that is?
And I,
It's an eye, okay? They introduced a viewing source right here. And so they decided to watch the electrons go through the slit and see what happened when they came out the other side. Y'all, when they watched electrons go through the slit, the electrons did this. They behaved like matter. They didn't behave like waves. When they did not watch them, they did that. The electrons behaved differently when they were being watched. Does that not sound like sci-fi? Yeah, it does. Okay? In order to watch them, you had to introduce wavelengths to watch them, didn't you? And that disturbed them and made them behave differently. Okay? So it's a really abstract concept, but this is what happened. They behaved differently when they were being watched. Now, scientists were, this is just one experiment with electrons that scientists are trying to explain. Another thing they're trying to explain was something called black body radiation. Black body radiation is the emission of light from hot objects. When objects get hot, they glow a certain color. That's not strange to us, right? Whether it's the eye on the stove or different stuff burning, there's different colors when it burns.
like when you're melting metal
Yes.
in a foundry.
Okay, when you're melting metal in a foundry, maybe we've only seen that on a TV show of like how stuff works or how it's made. I hope y'all watch those shows. They're kind of fun. But yeah, when they're heating up metal and there's different colors based on what the source of the metal is. And scientists were trying to relate the color that hot stuff glowed to how much energy it was. And I think that would make sense to you because don't we know that as the light gets whiter, it's hotter? Okay, it's all hot. It's all going to burn us. But the different colors of light means different intensities of it. And so relate it to the energy. Hang on, I got a handout to give y'all. And I'm getting to this. It's kind of a summary on the front page, and we're going to talk about some of these. Another thing, I don't think I have it on here, but it's in your book somewhere. Scientists were looking at something they named the photoelectric effect. And y'all, the photoelectric effect is when certain metals, when you bombard the metals with high energy, these metals will emit electrons, okay? But it takes a certain amount of energy for this to happen. And so you bombard the metal with energy, and the metal gives off electrons, and then you can detect the electrons. And so they were making measurements like, how much energy does it take to make this metal emit electrons? And so maybe you're like, who cares? What is that about? Well, y'all, photoelectric effect in these studies, do y'all have a garage door at home? Anybody? If you don't have one, you've been somewhere that has a garage door. And y'all know that there's sensors on the ground of a garage door. And if something walks in front of that sensor, did y'all know this, that it stops the garage door from closing?
Yes, I did.
Okay. Those sensors, that technology comes from studying the photoelectric effect. Okay? So there's sensors on either side, and as long as they can read that there's a beam, as they're receiving energy, then they're okay to let the garage door. But if anything gets in front of that, whether it's The dog walks in front of it when you're trying to close the garage door. That's what happens at our house all the time. And the dog goes in front of the sensor and stands there. And we're trying to back out and shut the garage door, and he would just stand there and look at us. And we're like, you gotta move, because I can't shut the garage door till you move. It can be a piece of dust. It can be a bug there, but it will not let you shut the garage door. Also, photoelectric effect, any kind of night vision. The fact that we have night vision, whether it's cameras or scopes or what have you, that technology comes from the photoelectric effect. If you have, y'all have solar powered calculators? Like this is a solar powered calculator. That technology comes from studying the photoelectric effect. So that's where, I mean, these studies led us to all that.
That's how solar panels were invented.
Huh?
Is that how solar panels were invented?
Yes, yes. This study led us to have solar panels. Okay. So, moving on kind of to this worksheet or note sheet. Niels Bohr, we talked about him and his model of the atom. He developed a theoretical explanation for the emission of hydrogen. Okay, what is that talking about? Well, y'all, how many protons does hydrogen have? Do y'all know? You'd know by looking at the periodic table. A hydrogen atom has 1 proton. Hydrogen atom has 1 electron. Okay? All of these studies are trying to explain electrons. Bohr studied hydrogen because it is the simplest system to study. It only has 1 electron. When you apply energy to a hydrogen atom, this electron, and y'all imagine this electron is simply orbiting the nucleus. Okay? That's not what it's doing. We don't know what it's doing is the answer. But we're going to imagine it so we can explain this, that this electron is just orbiting the nucleus like the planets orbit the sun. Okay? When that electron gets excited, that electron will jump higher away from hydrogen. Like maybe it jumped. Imagine that's a complete circle. I didn't do that very good. Imagine when that electron gets excited, it jumps to here. Okay? And one of the interesting things from their study was they said the electrons can only jump to allowed to certain places. Okay? In other words, the electron cannot hang out in the middle. Okay? And so the energy had to be in certain chunks of energy. And so the electron can get excited and move out to a higher orbit. Well, the further it is from the nucleus, that's more energy. It can't stay there. That electron is going to get rid of the energy in the form of light. Is it kind of coming back to why we did light and wavelengths and okay? And so the light that it released, because different colors of light have different types of energy. And so the light it released is related to, was the electron going to go from here to here? Or was the electron going to go from here to here? How far is it moving to go back where it wants to be, to what's called its ground state? Okay, so what's with this? I'm going to pass out to y'all. This is called a spectroscope. And I'm pass out. Take one pass out. Let me get you a blue one.
You know, we didn't worry about this. I think we might actually be de-lighted.
Okay. I'll give you a courtesy laugh. How's that?
Okay.
So look, mine looks a little different from y'all. But, I mean, you guys get the gist of it. Here you go. Look through the small end. You can look at the lights in the room. Okay? But y'all, what's more interesting, look at the window light.
It's like a prism.
Yeah.
Oh, yeah, yeah.
Y'all, when you look at, let me turn the overheads off. And the window might block some of it. When y'all look at the window light, do you see how it's Roy G. Biv all blended together? Do y'all see that when you look at the window light? Okay. Because the window light, obviously, that's from the sun. The sun emits all wavelengths. Okay? But when we take these and we look at artificial light, so that's what I'm gonna do here. And now, you're not gonna be able to see it, even Ethan, as close as you are. Y'all, to look at the light here, you have to get up, and you gotta be like 3 or 4 feet from it. Okay, so you're welcome to get up and come and look at it if you want to. But, let's see. This is hydrogen. This lamp, this is what Bohr studied. Okay, he had a light source, and this is filled with hydrogen. And when you turn on the electricity, the hydrogen gets excited. And so what happens, y'all, is those electrons start jumping up to a higher orbit, and they fall back down. And what we see with our naked eye, we just see a cool looking lamp, right? But when you take your spectroscope and you look at the light through the spectroscope, y'all come up here and look at it. When we looked at the window, we saw the rainbow. But just kind of get around and maybe then move and let somebody else have a turn. And so watch how I do. Y'all see how I'm kind of going left and right? You want to get the light coming through the slit on your spectroscope. And move your head left and right to get the intensity right. Do y'all see it producing lines on that ruler? You ought to see 4 lines. Like, I can't even see it. You're going to need to be closer, William.
Yeah.
I mean, y'all don't be afraid to get up here on it. It's not an eclipse, right? Are y'all ready for that for Monday?
Oh, my man,
When did they supposed to have it? Like
Monday. In a week.
They supposed to have like glasses for that.
Yeah.
You don't have to
I've
have
got some of
glasses.
them. You can look at it like this, but don't.
No! Don't do that.
That would make a blind.
No, look, what I'm going to do is use cardstock. Look online, and you poke a hole in the cardstock. And so you're not, have one piece of cardstock that's solid, one piece with a hole in it. And then just adjust it so that the light coming through the hole is reflected onto the cardstock in front of you. Small hole. Take a thumbtack, and real nice, and you'll see the eclipse on the paper. That's what I'm going to do. Or buy glasses. But do not do what Wesley says. Don't do that. Okay, did y'all see the line spectrum with the hydrogen? Okay. So, what you're seeing, y'all, what this little plastic thing in your hand does is it takes the light. No, y'all can hang on to them. I'll collect them. We might leave them out so that tomorrow's class, they're out there for tomorrow's class. This spectroscope does like the prism does, or like those when you have glass that's cut with edges. It takes the light that we see with the naked eye that just looks, what, kind of purple pink, just a cool light bulb, and it breaks it into certain wavelengths, okay? And so what you're seeing in here are the 4 wavelengths that hydrogen produces. And so y'all, what Niels Bohr, that's what it says on your sheet. He studied hydrogen. Niels Bohr came up with a mathematical formula. Isn't so much about science being able to explain it with math, being able to calculate it. And so Niels Bohr developed a formula. Don't worry, we're not going to do the calculations. Y'all could do them, but in my mind, it's just doing math for the sake of doing math. And I'd rather calculate grams and moles, because to me there's a purpose to that. Okay? We're not going to do the calculations. But Bohr was able to calculate, look, that when the electron moved from here, which is defined as the second orbit, to here to the first orbit, that this wavelength was produced. And then when he looked at it through a spectroscope, y'all, he found that wavelength on the spectroscope. And then Bohr said, okay, what if the electron moves from here to here? What if that's the transition? And he used his formula to calculate a wavelength, and then he looked through his spectroscope, and guess what? That wavelength was shown in his spectroscope. What if it moves from here to here? Well, that's a different wavelength. And so what Bohr was able to do was those 4 lines that y'all saw when you looked at that, he was able to have a mathematical equation that would calculate those 4 lines. But it only worked for hydrogen. That was the trick. when you had other elements, so look, that's hydrogen, and hang on, because I left that on a long time. It's kind of hot. I'm gonna,
I'm guessing the energizing it also created heat as well as light.
yes, yes. This is helium, which has 2 electrons, y'all, that are transitioning. And so with our eyes, we can tell it's different.
Yep.
But y'all, if you looked at it through a spectroscope, it's going to have a different line spectrum. I don't know if I made it clear. What y'all see in that spectroscope is the line spectrum. Okay? And so that's helium. And
Definitely different color, and that's for sure.
yeah, definitely a different color.
Probably different layers.
And so we're familiar with, y'all, the lights in Las Vegas, right? I mean, maybe you've never seen them, but you've seen pictures of them, okay? And so, y'all have heard it said neon lights?
Yep.
What's that song? Y'all want me to sing on my stuffy nose? Say the neon lights are bright. Come on, Ethan is rolling his eyes. Have y'all heard that song?
Nope.
The neon lights are bright. I'm recording this. Maybe I'll just send it to Anna so that y'all can't hear it. Anyway, y'all, true neon, if it's neon in a light, that's the orange lights, the really bright one. Okay? But obviously, if you wanted the purple color, you'd have hydrogen in the lights. And now, those are expensive lights. So, a lot of the colorful lights we see today, y'all know it's just a light bulb with like a green film on the outside. It's not. I got one more I can show you. This is mercury. And I think that's really pretty. Okay?
I'm feeling kind of blue.
Huh?
Frankly, I'm feeling kind of blue.
Okay, yeah, that's a pretty blue color.
What that one is?
Huh?
What that one?
Mercury.
I like that one.
I like that one too. And I like hydrogen because purple's my favorite color. But I like those two.
Seems like you got a little purple in the middle though.
Yes, it does, through there. Okay, so, what are those colors resulting from? In every one of them, it results in electrons. Some of them are here, some of them are here. Because mercury, y'all know mercury, it's got 80 electrons. It's got 80 protons and also 80 electrons. And so that light of mercury, you've got electrons way out here. And when we turn the light switch on, those electrons get excited. And they jump up to higher orbits, and then they fall back down, and they have to release light in order to fall down.
So I guess they might release a lot more light than hydrogen was there.
It depends on what you can calculate it. As far as the energy of them, let me show you all this. Get it lit. Y'all ever heard of a flame test? You ever heard that? Did y'all do it in high school where y'all burned salts and they produced certain color flames?
I think so.
No?
I think we did.
Okay, so here. What I have in these little bottles, like this is, what it is I took barium chloride and I dissolved it in water. And now it would be clear. I know it doesn't look clear right now. That's because I have these wooden splints. They're like little popsicle sticks, and they've been soaking in the salt. And so this wooden splint has been absorbing the barium chloride. And then I'm going to put it in that Bunsen burner, and it burns a little bit, and I put it back in here. And so that's where the color comes from. It's the burnt stick falling off in the liquid. Okay, but here's barium. Y'all see that kind of yellow-green color?
Yeah.
Okay, this is how fireworks get their light, get their colors.
Yeah,
It's different salts in them that burn. And you could. I used to try to do a lab with this, where y'all had to look at it, like Ethan would hold it, and your lab partner would be looking at it through the spectroscope and would write down its line spectrum. But what inevitably happens is the splint catches on fire before you get the line spectrum written down. It's kind of hard to see, but that's barium. Here's strontium. Notice how that one's been burnt a good bit.
Oh, it's orange.
Yeah. Orangey red.
More orange than normal fire.
Do y'all see I can also do this where I take those evaporated dishes and I put ethanol in the evaporated dishes, because you can set ethanol on fire. And then I take these solid salts and like drop them in the dish. Do y'all see how that would look magical? Or maybe even like witchcraft? Okay, that's what all that was, y'all. It was just science, where they would take something and it would smoke and they'd disappear. It wasn't any magic, it's just science. It's just manipulating. Okay,
Yeah, smoke pellets.
they're observing. Okay, here's lithium. Similar to strontium, yeah? But y'all, even though to our eyes, it looks very similar to strontium, if you were to look at that through that spectroscope, it would look, lithium would look very different from strontium in the spectroscope, okay?
Because the wavelengths.
Because of the different wavelengths. And then this is copper. See the green to it?
Yeah, yellow, green.
Uh-huh.
Yeah, yellow.
Okay.
Stuff that burns clear. Like they have like
The-
happens at like NASCAR schools.
Like you can't even see it burning, like
Yeah,
not that
can't
it
see it
burns
burning.
white, but clear. Is it a fuel?
I think it is.
Do you know, Ethan? It's like you're trying to think of it.
I know you can burn, moonshine, it burns clear.
Okay, and that's gonna be
I think it's some
Ethanol.
sort
or ethanol burns like, it's a blue flame, it's almost hard to see. Moonshine, sometimes when you burn it, it's actually the methanol that's burning. I don't know, I'm not sure about that.
And methanol is methanol and ethanol are both forms of alcohol.
They are, but methanol makes you go blind, and ethanol just makes you be stupid. I mean, that's the truth.
Yeah.
Okay.
Ethanol is the type that.
If you have too much
that
of it.
people usually consume.
Okay, so, Bohr studied hydrogen, and let me take Anna, when she watches this, is going to know that it would have been a lot cooler to be sitting in class today so you could see all my. All right.
Is she like in the hospital?
No, she's not in the hospital. She's not. I think right now what she's dealing mostly with is no vehicle. Her vehicle. But she's okay. So you don't have to memorize this, y'all. I just want to show you. These are line spectrums for different elements. So when I was burning those in the Bunsen burner, and I told you like lithium and strontium, to us, they both look orange. But if you look at them through a spectroscope, they look very different. A line spectrum is like an element's fingerprint. What can we say about your fingerprints, Jeffrey, versus mine? They're bigger. Okay, yours are bigger, but your fingerprints are going to be different from mine, right? Yeah, they
And
would.
is it, they have different distances between the ridges and some.
That is not what I expected.
And some
Okay.
whorls, loops, or arches.
Yes, okay, the whirls and the arches and all that.
And the distance
So
between
our
the ridges.
fingerprints identify us. Y'all, this identifies an element. Have you ever wondered how we look at planets or stars and we say, oh, this is what elements are burning in that star? Because that's what we're told, right? That the atmosphere of Saturn is dangerous because it's this. Yeah, we've never been to Saturn. Okay? Scientists look at the light from the stars and they look at it through spectroscopes. They have much fancier spectroscopes than our plastic ones, but they look at the light, and so it's light of different elements, okay, so it's the certain wavelength, and then they compare it to these, like an individual element. And if whatever it matches up with, that identifies what elements are there. And this, I lost a lot. I mean, y'all could look at this in your book. When I took the picture, you can't see a lot of the lines. But, guys, this is sodium. Sodium has 2 yellow lines right there. Next time y'all are driving at night, we were talking about this earlier, the older street lights, think about it. Do y'all recall that the street lights are yellow? That's because there's sodium vapor in those streetlights. That's why they're yellow. And when you look at this line spectrum from sodium, oh, that's why they're yellow. Okay? And of course, the newer ones are those, what you call
LEDs.
them? LEDs and stuff, or, yeah, they're just brighter and bluer. Okay? But that's what a line spectrum is. It's a fingerprint for an element. So, any questions so far? Where's my hand on? Okay. Now, Niels Bohr studied hydrogen. He was able to come up with a mathematical equation, and he was able to calculate what wavelengths of light hydrogen would give off. But y'all, as soon as they took Bohr's calculation and tried to apply it to any other element, it didn't work. Because when you've got more electrons, they start to interact with each other and they behave differently. And so his equation didn't work. That leads us to halfway on your sheet. Do y'all see where it says the Heisenberg uncertainty principle? Have y'all heard of Heisenberg before? Heard of him? Or the next guy I talk about on there, Schrodinger? Weston, where have you heard of Heisenberg? Come on.
I don't know, Breaking Bad.
Breaking Bad. That's exactly where I thought y'all would have heard of it from. Have y'all seen that series, Breaking Bad? Heisenberg? Okay. It's a pretty good series. So look, I hope you will see, what's it called, y'all, in English? When you got, like he didn't, is it, you know how you have all those English things like poetic and foreshadowing and irony and,
We're talking about Schrodinger's cat or something
I'm
else.
talking about Heisenberg. Okay. Huh?
What about?
Okay, what about him? Yeah, that would help if I explained it. So, in the movie Breaking Bad, in the series, the main character, his name is Walter White.
And he was a
But
chemistry
when
teacher
he's
before.
selling drugs in the drug world, he's called Heisenberg. Like, they don't know it's Walter White.
A pseudonym?
And it's his, thank you, pseudonym. Y'all help me out with my words. It's a pseudonym. Okay, and in the drug world, he's Heisenberg. Look at what Heisenberg said. Heisenberg said it's impossible to know with certainty where an electron is and where it's going. You never know what that electron's going to do. Do you see why he picked that name? You didn't know what Heisenberg was up to. You didn't know what. Do you appreciate a little more of why that was his name? I mean, it was a legit scientific name. What's that called in literature? When there's more to the name than
Symbolism?
symbolism, is that what it is?
I think it might be.
That, I mean, that sounds good to me.
Maybe it's maybe metaphor. I don't know. It's hard
See,
to-
that's where I get confused.
Yeah.
But there's some symbolism in where the name was picked as Heisenberg, okay? And what it really meant. And so that's what this guy, his name was Werner Heisenberg, he said, you don't know where an electron is or where it's going. And so, like when we look at these orbits, and I keep saying, just imagine that it's moving around in a circle. Heisenberg said, you don't know how it's moving, okay? Maybe it's probably not just moving around in a single orbit. Then we come to Schrodinger. And that's what y'all heard William say a second ago, Schrodinger's cat. And these are names also that if you watch The Big Bang Theory, that little sitcom, who watches that?
I hate that too, but
Yeah. Y'all gotta watch some more things.
Yeah.
Who has never seen Breaking Bad and never seen Big Bang Theory? And that needs to be on y'all's list for like after you finish finals. Let me ask you this then, what do you watch? I'm not trying to be snarky, like, what am I missing? What are y'all watching that I'm not watching?
Criminal Minds?
Oh, I do like Criminal Minds. I watch that too.
I usually
Superstore?
I
Don't
usually
know
watch
Superstore.
cartoons.
And in all fairness, when Breaking Bad was popular, what year was that? Y'all were too young to be watching it. And so, y'all might think it's a really old show. I think it wrapped up, we'd have to Google it. But y'all were too young to watch Breaking Bad when it first came out. My kids weren't allowed to watch it when it first came out. Anyway, Big Bang Theory.
Walter White was originally a chemistry teacher before selling drugs.
He was a chemistry teacher, yeah. Schrodinger, you ever heard of Schrodinger's cat?
Yeah, the cat could be alive or dead
Yes.
in another timeline. Or
Yes, if you have a cat in a box Is it alive or dead? And the answer is, you don't know. How are you, the only way, it's crazy, y'all. How do you know if it's alive or dead? Well, you have to open the box and look at it. But you can't open the box and look at it because what happens when you look at it? It quits behaving like a wave and starts behaving like matter. Do you see? That's where that discussion came from, y'all. Schrodinger's cat and this. Okay? These discussions were had amongst brilliant physicists. Okay, so you can't know where an electron is. That's what Heisenberg said. Schrodinger came up with this concept called the wave-particle duality of an electron, which, y'all, we've kind of talked about. When I was saying that double slit experiment, and I said when you fire electrons at those two slits, they behave like waves. But if you look at them, they behave like matter. They behave like particles. And so Schrodinger's equation takes into account this wave and particle duality of matter. And this opened a new field of physics called quantum physics. And that's what we're going to look at. Quantum physics is not classical physics. We're not talking about the ball rolling down the hill or, large objects. We're talking about electrons. Quantum physics gives us these numbers called quantum numbers. And the second sheet that I gave you lists the different quantum numbers. Y'all, what the quantum numbers are, they are solutions to Schrodinger's equation. Did you look up Heisenberg by any chance and Schrodinger?
I was trying to look up to see if I could find a picture labeled.
Oh, okay.
But I couldn't find
I found it one time, and now I Google smartest picture in the world with labels,
it.
and I can't find it again. I should have saved it the first time I found it. Okay, the quantum numbers are the solutions to Schrodinger's equation. Per your sheet that you have in front of you, do y'all see that there are 4 quantum numbers? 1, 2, 3, 4. Okay? Before I get too far, let me make a connection for y'all. And this is going to be based on your knowledge of high school chemistry. Have any of y'all ever done this? 1s2, 2s2, 2p6, it goes on and on and on. Ethan, yes. James?
I think so.
Okay. That's where we're going. For those of you who are like, well, no fair, I've never done it before. I'm about to show you how. It's not hard, okay? Y'all, this right here, 1s2, 2s2, 2p6, these are Schrodinger's quantum numbers. These are the solutions that are there. So let's go through them. Number 1, the Bohr model of the atom introduced us to what's called the principal quantum number. Y'all, the principal quantum number is labeled as n, okay? And the value of n can be anything from 1 to infinity. Has to be a whole number. So n can be 1, 2, 3, 4, 5, 6, 7, etc., etc., etc. Okay? On your sheet there, I have a little dot drawn. And so what you can add around that little dot are orbits. The orbit you draw closest to that dot, that is n equals 1. And then draw you another one. That's n equals 2. And then another one, n equals 3. And just as many as you can get. But do you see each of those orbits is a principal quantum number? On your sheet, I tell you that the value of n tells you about the size of the atom. Can you see that with my picture? That if n is equal to 4, the atom's much bigger in diameter than if n equals 1. Okay? And so n tells you about the size of the atom. What am I drawing here? Periodic table. Okay. there's period numbers down the left-hand side of the periodic table. Now that's N. So if I said N is equal to 5, I'm talking about something in that line. Okay? And so those are the values of N. 1, 2, 3, 4, 5, 6, 7. These here at the bottom, I wrote their N numbers. This is N as 4, and this is N as 5. Okay, and they're written on there. All right, let's do the second quantum number. The second one is known as the angular momentum quantum number. And I need y'all to fix something because, do y'all see on your sheet where I say 2, angular momentum quantum number, comma? That is an L. And look, that L should be like this. It should be more like a cursive L. On your sheet, it looks more like an italic L. Okay, but it's going to be that L. And I came in and printed these in a hurry this morning and didn't fix that. L can be anything from 0 up to N minus 1. L tells us about the shape of the orbital. The orbital is where the electron is, and L tells you in what shape is that electron going to be found. The value of L, I have this on your sheet, has a corresponding letter. If L is 0, that corresponds to an s orbital. 1 corresponds to a p orbital. 2 corresponds to a d orbital. And 3 corresponds to an f orbital. Okay? Y'all, that's the only letters you have to worry about. Oftentimes I get asked, what comes next? It doesn't matter. Okay? There's nothing beyond that. But what comes next is you just pick up with the alphabet. Okay? But that's the only ones we have to worry about. Now, how does L tell you about the shape of the orbital? On your sheet, do y'all see that I have 2 orbitals? One's called an s orbital, and one's called a p orbital. Do you see in the middle of an s orbital there's a strong dot? That's the nucleus. What you have around that nucleus, I'm going to draw it over here. This is called a density chart. So where the dots are, where the most dots are, is your most probability. Okay, do you see what I'm saying? It's an electron density map, is what it is. So when you're looking at an s orbital, and if you could take all those dots and make a shape with it, realize this is 3-dimensional. Do you see an s orbital has a spherical shape? And so when an electron is in an s orbital, that doesn't mean it's moving in a circle. That means it's moving around somewhere in that sphere. An s orbital has a spherical shape. Okay? The next one shows you a p orbital. Do you see the strong dot in the middle?
Yeah.
And then you have the electron density on either side. And so typically p orbitals, do y'all see we could take that electron density map and we could draw something like this? Okay? That's referred to as a dumbbell shape. I know it doesn't really look like a dumbbell, but that's what it's called. Okay? And so when you have an electron in a p orbital, that doesn't mean it's moving in a figure 8. That means somewhere in this dumbbell or that dumbbell, that's where the electron is. It's just moving around in there. We don't know where. Okay? And a great story I heard about a p orbital one time that I think helps. It related to me, and hopefully it'll help y'all. Guys, do you see that if I took 2 Coke bottles and I put them mouth to mouth, that they would have the shape of a p orbital?
Yeah.
Okay, now, that's the orbital. Put a fly in the Coke bottles. The fly represents the electron. And if we sat the Coke bottles right here on this desk, and we left the room, and then outside the room, y'all, we couldn't see in here, but we had a discussion about where in the shape of the room is the fly, we would all say, well, the fly is most likely on the front table in this shape. Do you see? Do we know if the fly is moving around? We don't know what the fly is doing, but we know that the most probable location for the fly is in those Coke bottles, the shape of a p orbital. Is there a small chance that the fly is actually not in that p orbital? There's a small chance that it flies over somewhere in the corner of the room. But the most probable location for the electron is in the Koch boss. Okay, so that's what a p orbital tells you. A d orbital, I don't have that on your sheet, but I'll draw it. Most d orbitals look like this. I'm going to take a picture from your book. We refer to that as a clover leaf shape. Here they are. Okay, that's some d orbitals. It's hard to see because it's like gray orbitals on a light blue color. But do y'all see, there's different ones, but do you see basically they have this clover leaf shape? This one's a little different looking. There's one. Y'all, these shapes, again, they come from solutions to Schrodinger's equation and graphing those quantum numbers. That's where they come from. Okay? So, here's your periodic table. These numbers I have written down the side, that's N. The periodic table is also organized by the L, the one we just talked about, the angular momentum quantum number. Y'all, groups 1 and 2, that is L is equal to 0. L equals 0 corresponds to an s orbital. Up there in the top right, helium, that is also an s orbital. Okay? This block right here, do y'all see this block? That is L is equal to, 1. L equals 1. Those correspond to the p orbitals, the dumbbells. This big triangle in the middle, y'all know those are all transition metals. That corresponds to L is equal to 2. Those are the d orbitals. Those are the clover leaf. Sometimes you will hear it referred to as d block elements or p block elements. Okay, and it's referring to the block from the periodic table. These at the bottom, what's their L value? 3. What's their letter for their orbital? F. Do you see why when I get asked what happens after F? Well, nothing, because that's as big as our periodic table is right now. Okay, and so that's where it stops. Okay. I know y'all are writing. Y'all, anytime on this, if I jump to a new slide and you were like, I didn't get all that, you can just say, hey, would you go back? Would you show me this slide again? Whatever. Okay. Let's put these first two quantum numbers together before I do the third one with you. Guys, if n is equal to 1, I'm telling you that, n is 1. According to your sheet, the value of L can be anything from 0 up to n minus 1. So if n is 1, L can only be 0. Okay? If n is 2, what can L be?
1.
Yes. Who said that, Weston or James? Yes. Do you see it can be 0 or 1? Because it can be anything from 0 up to n minus 1.
So it just can't be 2 or more.
It cannot be 2 or more.
Okay.
Okay? If n is 3, what can L be?
0 to 2.
It can be 0, 1, or 2. If n is 4, what can L be? I kind of ran out of room here, but
0 to 4.
0, 1, 2, or 3.
Oh,
Yeah. Make sense? Okay. What does N tell you about the size? What does L tell you about the shape? Remember, zeros correspond to S shapes, right? Spherical. Ones correspond to what shape?
An hourglass or?
The P, the dumbbell.
Yeah.
Okay. I could see where it's an hourglass. 2 corresponds to the D, the clover leaf. And I don't know what an F looks like. If you read the book, it'll tell you it's beyond the scope of this book. So it's beyond the scope of me too. I don't know what an F orbital looks like. Okay? Very complex. All right, let's do the third quantum number, and then we're going to come back and add to this chart. What's the third quantum number called? Magnetic quantum number? You're looking up F orbitals, aren't you, John?
Mm-hmm.
I think they're like waves and all kinds of. The magnetic quantum number is labeled as an ML, M with a little L subscript. And y'all on your sheet, y'all see under number 3A, it says can have a value from. Do y'all see that? Y'all, it looks like it says can have a value from 1 to -1. That says from L to -L. Again, it's the wrong font. It says can have a value from L to -L, including 0.
Italicizing might help in this case.
Well, yeah, but I'm going to have to change the font because that italic L just goes like this. It just leans a little bit. All right, so look, go back to the sheet. The value of ML, I just told you, it's from -L to +L, including 0. If L is 0, ML can only be 0. If L is 0, ML can only be 0. Y'all, what I'm telling you is that it only has one possible orientation in space. If the orbital is a sphere, y'all, it only has one orientation in space. If the sphere moves, you cannot tell that it's rotating. It's just one orientation. All right, if the value of L is 1, then what I just told you is this can be from -L to +L, including 0. So do you see that the possible values here for the ML are -1, 0, and +1? For N is 3, if L is equal to 0, what's ML? 0. If L is 1, what's ML? -1, +1, and 0. Y'all, it does not matter what order you put them in. Okay? What's important is to recognize there's 3 numbers here, and that's going to come full circle eventually. All right? If L is 2, you got to hit every number in between. How many possible values go here? 5 possible values because you go from -2 all the way up to +2. There's 5 possible values. Okay? And I'm just simply going to stop there because on that chart, because I ran out of room. But I want you guys to realize there's a chart like this. Hang on, I'm going to find it. In your book. Ethan, where is it? I think I've already skipped it. Oh, shucks, y'all. It's on page 281 in your book, and I only did up to n is equal to 3, but the one in your book goes all the way up to n equals 4. But y'all, I just wanted you to see where the numbers came from, and it makes answering some of these questions a little bit easier. Okay? Now, for just a second, let me go just a little bit further with you, okay? I'm going to hold off on the spin quantum number. And because I'm trying to keep everything on my iPad today so that Anna can see it, I want you guys to take this image and I want you to overlay it on the periodic table. Okay? So imagine this is overlaid. We're going to read the periodic table like you would read a book. Y'all, that means you read it. You start at the top and you go left to right, one line at a time. Do you see what I mean is you read hydrogen to helium, then you would read lithium to beryllium to boron, carbon, NOFNE, and then you go to NAMG, ALSIPS, CLAR. Do you see what I mean? One line at a time. Okay? And what we're going to do is we're going to take this. Do y'all see that hydrogen and helium, according to this diagram, they are 1s. Okay? And so we are going to write them in order from lowest energy. I'm going to put 1s at the bottom because it's the lowest energy. And we're going to build it up as we read the periodic table. We're going to build this up. So hydrogen and helium are 1s. After you read those two elements, you go to what element? Lithium and beryllium. Do you see that those are 2s? Take that diagram that I had a second ago and overlay it. Those are 2s. Okay? I want you to see this because I want you to be able to do it no problem. Okay? After beryllium, what element are you moving to? Boron. You're still on 2. You're still on the second period. But do you guys remember that this block over here is called 2p? These are the p's. So do you see after 2s comes 2p?
So we go by the numbers over there. The P number.
The 1 and the 2 is the number over here.
Okay.
And we're also remembering, y'all, that groups 1 and 2 are S. Groups 13 through 18, except helium, those are P's.
So hydrogen and helium are S1.
Right. But we would say 1S, Weston, instead of S1. Okay? After boron through neon, sodium and magnesium come next. What do I write on my 3S? After sodium and magnesium, magnesium C is number 12, right? What comes after 12? 13, 3P. 3P. Do you see that 3P takes care of aluminum through argon? What comes next? 4S. Okay, I'm going to stop there. I'll see you Thursday. Okay?